Welcome to this introduction of system dynamics as a method to assess disruption on construction claims. This video will show you how system dynamics works and how it can often help where other methods are no longer effective. And to do this, we will start by taking a closer look at disruption. This is the situation that you may find yourselves typically in at the end of a project. You will have been able to recover your baseline costs, and if you're lucky, the cost of variations and even of prolongation. But this will still leave a large chunk of your money on the table. Now, very often the temptation will be to claim that all of the overrun was disruption, but maybe you will be more sophisticated and use methods like the measured mile. Either way, historical data shows that typical recovery rates for disruption claims have been very low, on the range of 5 to 10%. Now, our proposition to you today is that system dynamics radically changes this picture, significantly increasing the recovery rates in disruption claims. Before we launch into it, just some definitions to make sure that we're all on the same page. When we're talking about disruption, we're talking about requiring additional resources to complete the same amount of work. For example, if you have to install a pump and it should take 20 man-hours, if it took 40, that is disruption. So we really are talking about efficiency losses. And these can come in two ways. First, through productivity losses. People are working more slowly. And second, through additional rework. So if we want to understand how disruption arises and spreads through complex projects, we have to understand the nature of the different factors that can impact productivity and work quality. Now, there's dozens of these factors and they're well documented in the literature. We will focus on these 5, which we will describe as we go along. To understand how they work, we need to start by the basics of how project work gets done. And it's, at a very high level, very simple. You have a scope of work that needs to be done. You apply manpower, that manpower works at a given productivity, so the work gets completed. And then, of course, you keep adjusting your manpower based on your progress and your planned sequence of activities, so that you always have the optimal number of people working on your project. Now, this would be an optimally planned and optimally executed project. But of course, reality is always more complex. So let's assume that now this project suffered from a disruptive event. For example, the demobilization of a large part of its manpower, and which will be remobilized a couple of months later. The direct impact of this event, as just stated, will be a severe reduction in manpower. And the immediate consequence of this will be that the progress on the project will slow down. You will start to fall behind, which means you will have to implement some acceleration measures. Now, the easiest one to apply is probably to apply schedule pressure on the crews. Tell them to work harder, work faster, and this will probably help you to make up some of the delay. But it also comes with a side effect, and that is that when you tell people to work harder, they also make more mistakes. Now, they don't do this on purpose, obviously. These mistakes are hidden. Nobody knows that they're there. So now, when you have to do new work based on the work that you just completed incorrectly, you will find that your work proceeds more slowly and that you're also making more mistakes. In other words, you will be disrupted. But the story doesn't end here. As we said, a couple of months later, you'll start to remobilize. But not all crews will remobilize at the same speed. So that now, even though you may, for example, have already back half of your workforce, only half of that may be able to work fully efficiently, because the other ones will depend on people that are not there yet. Again, you will be disrupted. It gets worse, because now people have to go up a learning curve. They have to reacquaint themselves with the project, its procedures, the state that they left it at. If new people are hired, it's even worse. Again, disruption. So all of this disruption, again, has you falling behind. So you have to implement additional acceleration measures. For example, this time, you may be deciding to add additional manpower. Yes, you know that this will be disruptive because these additional people will work out a sequence, but you're hoping that just by the sheer number of people, you will be able to make up for the delays. And of course, now you start finding those mistakes that you made earlier. It's been months since you made them, you even forgot what happened then, and suddenly now you're facing with this mountain of rework coming apparently out of nowhere. So you have to divert people to fix things. Again, you'll follow behind. Again, you'll try to accelerate. Again, you are disrupted. And of course, we have to keep in mind that this event did not just affect construction. It also affected design and procurement. So now you will also find yourself probably that you don't have enough design drawings, enough shop drawings, enough materials to proceed with the works effectively. So again, disruption. So here we have looked at just a single disruptive event, and we have seen how the disruption generated by it just keeps going and going and going, rippling through the project all the way through its completion. Not only that, but its impact has also spread from the area originally affected by the event to all areas of the project. And this is still only one event. Complex construction projects are typically affected by many. This is an example from an actual project that we worked on a few years ago. These are all the changes that were proposed by the employer during just 1 year of this project. 750, a third of which was implemented. But even the 500 that were not implemented were disruptive. Contractors had to assess the proposed changes, they had to rope off given areas of the works in case the employer decided to go ahead with the changes. So all these proposed changes were disruptive. So now we have hundreds of different disruptive events, all of them with consequences that keep rippling through the whole project. All these moving parts, it's a mess. How can you keep track of all of this and understand what's happening and who's causing what? The human mind is unable to do this, but thankfully we don't have to be able to do this on our own because we have tools. And one of them is very good at keeping track of things, the computer. So what we can do is we can take these words that I just spoke, these images that I used, and translate all this logic into equations and integrate them all into a single computer simulation model that will then be able to recreate all the dynamics that I just described. And this, in a nutshell, is what system dynamics is. System dynamics is a computer simulation methodology invented at MIT in America in the 1960s. It was first applied to estimate project disruption and delay back in 1976 on a claim against the US Navy. This claim was very successful, so the resulting model was used on other applications, and here we are 4 decades later, where system dynamics has been used in hundreds of projects all over the world in all sorts of different industries: construction, aerospace, oil and gas, engineering, shipbuilding, the automotive industry, software, you name it. System dynamics models have also been the basis for over 40 major disruption claims worldwide, totaling over $20 billion in claim amounts. System dynamics has also been designated industry best practice by the Engineering Construction Risk Institute in 2009. In 2017, the Society of Construction Law included system dynamics as an accepted method for estimating disruption in the second edition of its Delay and Disruption Protocol. Finally, just a few weeks ago, the American Society of Civil Engineers awarded its Thomas Fitch Rowland Award to a paper based on system dynamics. So it has taken about 4 decades, but we can say that system dynamics has finally started to make serious inroads into the mainstream of the construction world. So how do we apply system dynamics to assess disruption on your project? Well, we start with the causal framework described earlier and translate it into equations. But now we have to make sure that the resulting simulation model describes your project, not just any project. So we gather as much information about your project as we can. Information, for example, about its bills of quantities, the characteristics of its manpower, its baseline schedules, and so on and so forth. We also gather information about its as-built performance, the amount of manpower employed at different stages, the progress achieved, the S-curves, etc. And we even gather some soft data about the project, the management philosophy. Was it focused on keeping costs down, or rather on staying on time? All of this information then is integrated into the simulation model so that at the end of this process, when it's set up and well calibrated, the model is able to recreate the actual as-built performance of the project. In this graph shows how manpower evolved over time on the project. The red dashed line is the actual as-built data for the project, and the continuous blue line is the output of the simulation model. So as you can see, the simulation faithfully recreates what happened in reality, and not just on one dimension, but on all dimensions for which we have data. So that when this model is well correctly set up and calibrated, it is the most complete, most thorough, most accurate, most plausible explanation of what actually happened on your project that you could possibly get. But of course, this is very nice, but it doesn't answer our question yet, which was how much of what happened, how much of the disruption was caused by the other party, typically the employer. But now, we're just one step away from being able to answer this question. Because all we have to do now is just take our model and remove the disruptive events that were included. All those disruptive events that happened that were caused by the other party, typically the employer, the demobilization of the workforce, the design changes, all of that we remove, and we leave in, we don't touch the characteristics of the project, of the manpower, all of that stays the same. We simply remove the events and press the simulate button again, and we get a second simulation we call the but-for simulation. What would have happened but for these disruptive events? In other words, what would have happened if these events had never occurred? And now we can answer our question, because if we focus on the top right graph, the red and the blue lines, the data and the as-built simulation, tell us how many resources were actually spent on the project. And the green line, the but-for simulation, tells us how many resources would have been used without the disruptive events that were caused by the employer. So now we can answer a question, and it's clear that the employer was responsible for the difference between the red and blue and the green. That one would include direct costs and all of the associated disruption. Now at this point, it is important to distinguish between the but-for and the baseline of the project. They are not the same because the but-for simulation still includes within it all the unexpected inefficiencies for which the contractor was responsible. All the disruptive events, the underestimations, under-execution, all of that is still included in the but-for simulation. So, as you can see, system dynamics is not a method to blame everything on the other party, but rather a method to fairly assess the responsibility of each one. And before we move on, one other point. As we have seen before, delay and disruption are really sides of the same coin. You cannot have one without the other. So system dynamics models used to assess disruption also simulate the project schedule. So they can be used to support delay claims as well. But returning to disruption. We just said that we could assess the overall disruption in the project by just removing all the events. But of course, we don't have to do this all in one step. We can instead take them out one by one, which is actually what we typically do, so that then we can assess the disruptive impact of each separate event that we're claiming against. Which of course makes the disruption claim much more defensible. So this is how we use system dynamics on disruption claims. And here's why we say that system dynamics can help where other methods cannot. All assessment methods for disruption need to satisfy three requirements to be defensible. First, they need to establish causation. And system dynamics models do that because they are based on causation. They show how different variables of the project interact with each other. So with a system dynamics model, we can actually develop a detailed causal narrative showing step by step how each disruptive event affected all the areas of the project. Also, assessment methods have to quantify the resulting damages. Now, system dynamic models capture the full nonlinearity of disruption, all those consequences of the consequences of the consequences, keeping separate those from one event from those from all other events, and especially separating consequences for which the employer is responsible from those for which the contractor is. And finally, assessment methods need to be testable. You need to establish how accurate they are. Now, system dynamics are mathematical models, so you can actually quantify the deviation between the results and the actual as-well performance of the model, and you can actually establish the uncertainty range surrounding the estimated claim amounts, so they are fully testable. Now, this is all the theory about system dynamics, so we thought we would leave you with a few examples. We will alter the names of the project for confidentiality reasons. So, the Tuxedo Park was a commercial development, design bid build project in the MENA region, budgeted at about $1 billion, which overran its budget by $500 million and finished 2.5 years late. The contractor knew that the employer had substantially impacted the project, but was unable to prove it using conventional methods. Tried to use the measured mile, but he couldn't find an unimpacted area of the project to base it on, so that didn't work. So he eventually turned to system dynamics. We ran an assessment the way that we just described, and it proved that 60% of the overrun had been caused by the employer. Now, this claim did not settle. It went all the way through international arbitration, where the system dynamics evidence was presented to the three-judge tribunal, and this tribunal eventually awarded 100% of what was being claimed to the contractor, the full 60% of the overrun, claiming that the system dynamics evidence presented to them was the most accurate and most plausible evidence that they had seen. A second example was the Petrochem refinery claim. Here, we're talking about a design bid build subcontract within a major oil and gas infrastructure project, also in the MENA region, budgeted at about $300 million. By the way, this was a contract that involved some Korean companies, but we will not say in which role. This project suffered significant overruns, and our client, the subcontractor, argued that these had been the responsibility of the main contractor. They entered into an initial round of negotiations around disruption, but They failed to reach a settlement, so then the subcontractor decided to engage CDS to produce a more defensible disruption claim. Now, at first, the main contractor opposed using system dynamics to produce this new claim, saying that it was not based on data and it would take too long. However, our client was able to prove that these worries were unfounded and, moreover, started to share the information about the assessment with the main contractor, the steps being followed, the data being used, the questions being asked, so that within a month of starting the assessment, the main contractor saw the rigor, the thoroughness of the assessment, and both parties reached a settlement even before the assessment was completed. We hope that this presentation showed you the new possibilities offered to you on disruption claims by the use of system dynamics. Thank you very much for your interest.